right, week 6 is on plate movement, and I thought I would just create this little screencast to go over the notes, just to make sure you are clear on how the story goes. I think the videos are pretty good, but first of all, our story about plate movement and if plates move starts with Alfred Wegener, at least in our current timing. I believe that the Greeks and had some kind of idea about it, but it's not something that we really had a good science on until the last couple hundred years in studying geology. So our story for us is going to start in 1915 with Alfred Wegener because he did propose continental drift. Notice it's a hypothesis. That's because it was rejected. But he did have this hypothesis. He wrote it in a journal, which is a scientific journal that the other scientists read. And so he said that the continents had once been together to form a single supercontinent, and he called it Pangaea. And that it broke apart by continental drift. And then he said the continents are like ships, and they drift over the ocean or through the ocean floor. And this, of course, is going to be the part of the story nobody really accepted. But let's look at the evidence that he had for Pangaea. So his first piece of evidence is just if you look at the continents, a lot of the continents seem to fit a little bit, especially South America and Africa, right? So this little picture, you don't even have to change anything about the coastline. It is a perfect fit. And why would that be unless they were once together? The second one is fossils of the same organism that are found on different continents. And a lot of these fossils are like freshwater animals. They wouldn't have swam in an ocean that would have killed them. And so there's no explanation as to how you have these two fossils on both continents, because they would have had to have evolved in the same place. So the only explanation is that this landmass was together at one point, and they lived on that landmass together and then became fossils. And then when the continents spread apart, the fossils were spread apart. Another one has to do with geology, and especially, again, South America and Africa is a very big one that has a lot of evidence for. So on South America and Africa are these large rock formations that are of the same age and the same composition. And the only way these large rock formations would have been all the same is if they formed together at the same time. And then, of course, now they're split apart by an ocean because the plates moved. And then another one is just looking at, again, the fossil record and seeing that plants that would make up swamps covered a lot of North America. Look, this is Maine, right? So Maine has swamps. That's kind of weird, right? And then parts of Africa. This part of Africa is a desert now, but it has fossils for having been a swamp. And you can see more swamps in different places that they don't have swamps today. So the only explanation is that those parts of the continent used to be at the equator, right? So at the equator. Another one is another geologic formation. So we have these mountain ranges that go through Britain and Greenland and Scandinavia. And then this mountain range, it goes, the Appalachian Mountain Range, that goes to North America. They're all the same. This mountain range is the same age and the same height and made out of the same material. Again, the only explanation is that they actually formed because North America had crashed into Africa, creating this one. And North America and Greenland was crashing into Europe, creating this one. And then they broke back apart. So that just shows you, again, they were once together and now they're not. And then we have the last piece of big evidence is about glacial scarring. So see the arrows? The arrows show the direction in which a glacier grows. Obviously, we know glaciers come from the North or the South Pole, and then they would grow towards the equator. Now, really interesting, here's our Earth currently, And so there was a glacier all the way up at the equator on Africa. No, that's not what happened, right? There was a glacier all over India, where India is today. There's no way it would be a glacier there. It's way too hot. And even here in South Australia is really hot part of Australia. So there's no way a glacier formed where Australia is today. But we can explain it if India was down in the South Pole and Africa was pushed towards the South Pole and South America and Australia, all at the South Pole at one point, where the glacier grew over all of those pieces of land. And so that explains how India has shows scars of a glacier, because India used to be way, way down at the South Pole. Of course, now it's already way up it's in the northern hemisphere near the equator. So these evidence just show that the continents definitely are moving around and we're in different places than they used to be. But like I said before, it is a hypothesis because there was no proof for the mechanism or how the continents move. It's kind of seemed quite silly to most scientists to say that the continents drift or crash through the ocean like ships. So that is unreasonable, illogical, didn't make sense. So the hypothesis was rejected. It's not that they didn't think maybe he was right, but he just didn't have a good explanation. So this did not go into any book in school. No one talked about Pangea until 1962. So I just put this together just to make sure you kind of have an idea. Again, the proposal was that we had one single supercontinent Pangea, and here was the evidence for Pangea. So 1962, now we have new evidence by many scientists that finally brought together the idea that the continents really are moving. And so they rewrote the definition, and now it's called plate tectonic theory. And it states that the outer rigid layer of the Earth, which is called the lithosphere, remember that is the crust, and the upper part of the mantle is divided into a dozen plates that move across the Earth. And it's because of mantle convection. So we've already started to talk about the Earth has layers and that the core is really hot. That's going to be part of our story this week. So this was proposed and again written in those scientific journals. Other scientists read it and they've accepted it. And this is why it's in textbooks today and why I'm teaching it to you. So the main piece of evidence was discovered by really Henry Hess and Dietz, 1961, 1962. And their piece of evidence was the seafloor is spreading apart at ocean ridges. So if we look, this is an ocean ridge. Under the ocean is like an underwater mountain chain that we wouldn't know about except for we have sonar and we were able to do mapping of the ocean floor. And at the very middle of this mountain range is magma coming up, seeping up through the bottom, and then hardening into new rock. So this is what an ocean ridge is. And we see this all around the Earth. It's like the Earth has this, looks like a baseball mitt almost, where the ocean ridges are. So one of the ways we could tell the seafloor was spreading apart is that we were looking at the paleomagnetism. So remember we talked about how the Earth magnetism reverses and then is normal and then reverses. So this is what happened when we looked at the ocean floor. So at the ocean ridge right now, along both sides of the ocean ridge, it is normal. But if you continue to move away from the ocean ridge, it turns reverse. And then it goes normal. And on the other side, normal, reverse, normal. These are what we call mirror images on both sides. So what does that tell us? It tells us that the plates are moving apart, or the seafloor is moving apart. It's spreading apart. It's getting wider here. So that was one piece that told us. The other piece was if we actually gave it an age. So then again, if we look at the rift and we look at the age, it's exactly the same on both sides. 1, 2, 3, 4 million years. 1, 2, 3, 4 million years. Notice that at the ridge, it's new, and away from the ridge, towards the continents, it's old. This says that new is being made here, and it's pushing it out this way and that way. So again, this is what I'm showing you about the ocean ridge. So here's ocean ridge. See this red right here? It goes all down. This is the Atlantic Ocean. It goes all through. Now we're over in the Indian Ocean. And down around this way, they're like South Atlantic and South Indian Ocean. And then it kind of comes around in the Pacific. And then this is up through the Pacific Ocean where our ridge is. And so where the red is, it's all brand new rock. So that's an ocean ridge, and it's all over the earth. And then notice by the continents, it's the old rock. It's blue and purple. So at the ridges, this is where new rock is, and it's old rock that way. So here, the Atlantic Ocean is spreading apart and getting bigger. Over here, the plate is actually subducting, and the Pacific Ocean is actually getting smaller. We'll talk about that too. So that piece of evidence is right here. Seafloor spreading apart at ocean ridges. We looked at the paleomagnetism and the age, and that shows us that it is spreading apart in the seafloor. So the next piece of evidence we see is if we just looked at, like, where are all the earthquakes in the earth, in the world, and where are all the volcanoes? And what we see is this. So here are your volcanoes. Okay. Then here are earthquakes. The earthquake pattern really kind of starts to tell us the story, because do you see how the earthquakes go like this or go around this way? And then we have it like around this way. And then if you see, oh, look at our plates. So the plates match where the earthquakes are. The earthquakes are all around here. All around here. All around here, right? So we see definite places where we see earthquakes. So when we look at where the earthquakes are and where the volcanoes are, they're marking the edges of those plates. We also can even look at the earthquake pattern. And so where we find trenches is where we find deep earthquakes. And where we find ridges is where we find surface earthquakes. So again, this is showing you a pattern of depth. These are where trenches are. You probably heard of the Mariana Trench. It's the deepest trench in the Pacific Ocean. They have really deep earthquakes. Then over here, we have a lot of earthquakes at the surface. So this is more ridge pattern. And see, all this is all ridge, Atlantic Ridge. Remember, I just showed you where the ridges are? That's where all the surface earthquakes are. So it really matches this theory really well. And this just kind of shows you again where the plate subducts and it makes a trench. This is where you have deep earthquakes. This is also how you get islands, which I think is either next week or the week after. All right, the last piece of evidence that really shows plate tectonics is the fact that we have something called a hotspot around the Earth. There's several hotspots. You might think of like Yellowstone as kind of a hotspot. But the hotspot that we're going to talk about are the Hawaiian Islands. So a hotspot is just a place where magma seems to come up. It's not on the edge of the plate. It's like in the middle of the plate. But what it does show us is that the plate is moving. So when we look at the Hawaiian Islands, and actually you can see how the Hawaiian Islands actually are also part of the Midway Islands and then these islands here. So you can see Hawaii is just the last island that got made. But if we just looked at the Hawaiian Islands, if you look at the age, Kauai is 3.8 to 5.6 million years old. And then Oahu's 2.2, and Molokai is 1.3, and Maui is less than 1 million years old. And Hawaii is brand new. It's still growing. It's still on the hotspot. The volcanoes here are still erupting. And so what does this show us? This shows us that Kauai used to be over here on the hotspot, and that's how it was made, but then it moved away from the hotspot, um, and then Oahu was over the hotspot, and that's how Oahu got made. And then it moved out of the way, and Molokai got made, and Maui got made, and now we have Hawaii. So we can see that the plate is moving in a direction. So we know that the Pacific plate is actually moving this direction towards Japan. And this is really very great evidence and proof that the plates are moving. So with plate tectonics, what we found is, oh yeah, Pangea. Oh, that's right. So Alfred Wegener's idea of Pangea is correct, but the continents weren't drifting. The seafloor is spreading, right? So that was the big difference. So Pangea is also evidence for plate tectonic theory. So we will take back that evidence to support plate tectonic theory. So here it is again, right? The theory says that we have this outer rigid layer. It's broken up into distant plates. What proves that? Earthquake patterns and volcano locations that move across the Earth's surface. What proves that? C4 spreading is proving movement. Hot spots are showing movement. And then the fact that the continents used to be Pangea is movement. So this is all proof that the plates are moving and that they're broken up into plates. How are they moving? Why are they moving? How does this happen? So again, we now know about the core. It's hot. It's going to heat up the rock above in the mantle and melt the rock. And then we also know convective flow. It's just normal. Hot things rise, cold things sink. Like in the air, hot air rises, cold air sinks. In water, hot air rises to the top, the cold water sinks to the bottom. So even with rock or magma, hot rock goes to the surface, cold rock comes back down. And that creates convective flow. Convective flow is just that circulation flow. So we definitely see mantle plumes. Those are masses of hotter than normal mantle that just go to the surface. And so that's going to lead to volcanoes. And we also know that the Earth is unequally heated from within. So when we look at this, you might think, oh, it's all hot, but it is and it's not. It seems to be very unequal. There are definitely hotter places in the Earth and cooler places in the Earth. That's what really drives that thermal convection. All right, so we have that circulation, and you have those mantle plumes. That's what creates those hot spots. Otherwise, the magma is going to flow and push the plates around. So the two main ways the plates get pushed or pulled, in this case, is one called slab pull. So slab pull is, we know that the plates descend under other plates. So this would be a continent, and this is the ocean floor. The ocean floor is denser, so it sinks below the less dense continental rock. And so as it's going down, the gravity is pulling it even further. So it's kind of pulling the rock down into the Earth's surface. So that's called slab pull. Ridge push is, again, talking about those ocean ridges where it kind of goes up and makes those mountains. As the magma comes up, it pushes the rock out of its way and then hardens. Remember, gravity's kind of pulling it and the magma is going up. So the force is going to cause it to go this direction or this direction. So it's going to move away from the ridges. So at the ridges, you kind of have a push of the plates away from the ridge, and then you have a pull of the plate going down on the other side. So it's that combination that's causing that plate to move. So that's how plates move, because of the mantle convection underneath.